Hi! In this video, we'll be going through what are group actions and some examples of group actions. So let's first define what a group action is. A group action is you take a group and a set A, so it's a set, not a group. It could be a group, but we just need to consider a set. And we say that the group action is the function from G cross A to A. And then, so what this means is that you take an element in this two and it produces another element A1. And we just write the multiplication sign for convenience. But this function must satisfy some properties such as associative and the identity property. So we are saying that if we take G1 and we act it on G2 which acted on A, it is the same as the element of G1, G2 which is the element of G acting on A. And the identity element in the group will always send A to A. And so intuitively what we are saying is that we are permuting the elements in A by an action of G. So what does this permutation mean? Well, it means that for a fixed G, we can now define a map sigma G from A to A, which sends any A to where this G is acted upon. And this map that we define for every G will become a function, and this function is a homomorphism. So what it's really saying is this capital Phi is a map from G to the set of bijective functions from A to A. Then for each G is sent to little phi of G, and this little phi is defined to be sending A to another A. So this is the permutation, and this capital Phi is the homomorphism. So we'll take a note later after we prove these two facts on what does this really mean and how do we think of it intuitively. So now we can see that we want to prove that first is a permutation, meaning phi of G is a bijective function, and so we just need to find its inverse, and we can do so. And as a result, this shows that this is bijective and hence a permutation of A. And to check the next assertion that is a homomorphism, you just need to show that it respects group operation. And so what we are saying is that this permutation and this composition of functions are equal for every value of A in as an element of capital A. And so you just take a random A and just check that they are equal. And this proves the assertion of part 2 above. And so with that, now we can intuitively think of a group action as a way of permuting the set A with, so every element in G acts as a permutation. So it means that for each G, it acts upon the A and is sent to another A in capital A, so into the set. So you can really think is you're like shifting around all these elements in A around. And not only that, is that every action has a corresponding homomorphism corresponds to a homomorphism from G to the set of functions, bijective functions from A to A. So what we are really saying is that the actions of a group and the homomorphisms from group into the symmetric group are in bijective correspondence. So every action gives you a correspondence, and every correspondence from G to the symmetric group gives you an action. And this action, because it's in front of the A, we call it the left action. You can also define a similar notion for the right action, but we mainly deal with left actions. So some examples of group actions will be the trivial action, and so every element is just sent to itself for every G. And this is really saying that the permutation is the identity map. So if we say that an action is faithful if this permutation is injective, and what it's saying is that distinct elements of G induces distinct permutations of the set B, and the kernel of this action is defined as the element in G such that G times B equals to B for all B's. And so we are saying that the elements of G that fixes the elements in B. And we can see that the trivial action has a kernel of the whole of G, and so the action is not faithful when G is larger than 1. Because to be faithful, you need to be injective. So more common examples of group action that are very useful is what is known as the regular action. And it's really, your regular action means that it's an action of G onto the set itself. So it's G cross G into G. And the natural way to define this will be the left multiplication. And that's because you already have group operation, so you just need to do the same action as the group operation. And this is known as the left regular action. Another type of action that is commonly used is the conjugation action. And that's really saying that for A, you just multiply G in front and G inverse to the right. So it's again an action onto itself. So really, these two actions come into play the most, because most of the time when you want to prove something later on, we'll see, we take the action onto the group itself to prove something about the group. So these two actions are the most commonly used. But of course, it's good to have more knowledge of different types of group actions so that it can help you better understand how group actions work and when to use what actions to help you solve the questions easily. And you can really check this out in the textbook by Dahmer and Foote. So more definitions is that the kernel of the action is the set G such that G time acting on A equals to A for all A. And the stabilizer is the one G that fixes that particular A. So for each A, the stabilizer is all the G's that equals to A. So G dot A equals to A. And then the equivalence classes, or where G dot A ends up in, is known as the orbit of G containing A. And what this really says is that all the elements in B, such that there exists a G in capital G, such that B equals to G dot A. So we can think of the orbit as elements that A is sent to by G. And why do we call it an equivalence class? Is because by proposition 2 below here, we can actually show that the elements that A is sent to by G for some G in capital G is an equivalence relation. And so what it's saying is that the set A can be partitioned into these equivalence classes by the orbits. So the orbits are the equivalence class. And then we'll show that the number of elements in the orbits is actually the index of the stabilizers. So we'll first prove that it's equivalence class, and it's a really simple checking to check that it's reflexive. And if A is symmetric, is equivalent to B, then means A equals to G dot B. And so when you take the inverse, then it will equals to B. And so now B is symmetric, is equivalent to A, and hence the relation is symmetric. And if it's transitive, you can again check that the relation is transitive. And so what is really harder is to prove the last statement of the proposition. And it's not too difficult because we just need to find a bijection between the set of left cosets of the stabilizers and the equivalence classes of A, meaning the orbits of A. And so we let the orbits of A be denoted by CA, and we suppose B equals to G dot A, which now must be an element of the orbit. And so the left cosets of this will be G times the stabilizer of A. And this is the left coset. And then you can just take the map from B, go into this left coset. Because you know A will be in here. So this map is surjective since for any G in G, the element G dot A is the element of the orbit. And since G dot A equals to H dot A, if and only if the cosets are equal, the element H inverse times G is the element of the stabilizer, then this must mean that G times the stabilizer equals to H times the stabilizer. And so the map is also injective. And hence you have a bijection. And so you can actually say that the number of stabilizers is the orbits, the number of elements in the orbits. And as a corollary of that, we have the orbit stabilizer theorem, which states that the number of elements in G equals to the size of the orbit times the size of the stabilizer. And also a corollary, because of the equivalence relation, we can just say that the size of A is actually equals to the disjoint unions of the orbits. So the side, you just need to put the elements summation, the number of elements in each orbit. And the last notation to take note is we call an action transitive if there's only one orbit. So we shall take a look at some examples of what are orbits and what are stabilizers. And for example, for the left regular action, the stabilizer of X is 1 and the orbit is G. These examples that I'll be showing you, you can of course easily verify them yourself, and I urge you to try so that you get a better understanding of what is an orbit and what is a stabilizer. And for the left conjugation action on itself, we know that the stabilizer would then be the centralizer of X, and the orbit is just the conjugacy class of X. And if you were to act onto the set of non-empty subsets of G, then the stabilizer would just be the normalizer of H. And the orbits will be G, H, G inverse. And so, we can actually say that any one element conjugacy orbit, it only occurs if and only if G, A, G inverse equals to A itself. Because this is the conjugacy class. So it must equals to A only for all G. But this really says that A lies in the center of G. Because if this occurs, then it's by definition A is element of the center. Because GA now equals to AG for all G. So A is in the center of G. And this gives us a way to prove theorem 7, which states that the size of G now is the size of the center of G plus all of these indexes. And these indexes are the distinct conjugacy classes of G not contained in the center. So why is that so? Well, you can think of it intuitively, and the proof is written below. It's because for the center of G, we know that the left we can just use, we just need to use the correct group action, whether the regular action or the conjugacy action, to split up G into the various equivalence classes, so into the various orbits. So in this case, we just need to split up all the thing into the different orbits, and for each conjugacy class, the center will represent all those with ones. So if you're 1, then you're in the center, so you can take those out first, and whatever you remain is not in the center, and you can represent them by a representative called GI, and so the full set of the conjugacy class will then be denoted by the following. And because this partitions G, then we just need to take the summation of all these elements. And so the elements of this conjugacy class will just be the index of the centralizer of GI. And as a result of that, so you can just take a look at this action over here to understand the class equation. And because of that, we know that for the ones in the center, they're all ones. So it's just the total amount of elements in the center. And so putting them together, we get that the number of elements in G equals to the center of G plus the number of elements in the conjugacy classes. And this is known as the class equation. So that's all for this video, where I introduced to you what are group actions and what are commonly used group actions, including theorems such as the orbit stabilizer theorem and the class equation. I hope you have enjoyed it, and in the next video, I'll be doing Selous theorem and applications of it. Thank you for listening and have a great day. Bye!